So as mentioned in the email that I blasted out, if you downloaded the graphics.py file during class on Tuesday, then you got the wrong version, for which I apologize. Go ahead and just download it again. My D2L is uploaded, D2L is updated with the newest one. I think we are through. The error that you'll see is graphics window not found or something like that. So it's pretty obvious right from the get-go. So we've talked about void functions and fruitful functions. Fruitful functions return a value, like the result of a calculation. Void functions do not. You can chain function calls if you need to. A function can call another function, can call another function. A function can even return itself, call itself, which is called recursion. We're going to do a very simple little recursion problem. So open up good old idle. And we're going to write two ways of adding up all the numbers between 1 and 10. And put your name up at the top. Topic of this one is recursion. So you may as well do a save as. Place it in your favorite directory. Let's call it Sept14. No spaces. Sept14 REC for recursion. I'm sure we'll create another file in a minute. Different one once we've moved on topics. Okay, so let's write a function that will add up all the numbers between 1 and the specified upper value. What do I mean by that? If you say 10, it's going to add up 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. If you say that you want them up to 20, it'll go up to 20. If you say you want them to go up to 1,000,000, whatever. Okay. So we're going to put our functions up here. So I'm going to give myself a little bit of space, and let's find out how far the user wants to go up. Max is such a bad word. I type it in and it comes up purple, and I realize I need to call it something else. Let's call it limit. Limit is equal to the integer version of our input function, which says sum up to what value? Then we're going to write two different versions of our summation. So let's do sum1, that sounds odd, is equal to sum loop up to the limit. We're going to write that function. That's not a function that's built in. And then sum2 is equal to the sum recurse. How about just sum REC? Make it easier to type. Limit. And then we'll print them both out to make sure that they're the same. Print sum1 equals %d, sum2 equals %d, end quote, followed by a parentheses, followed by a pair of parentheses and one more parentheses, and in there, what are we going to put? Sum1 and sum2. Like that. All right, now those functions don't do anything, do they? Right? Okay, so just to get this code to compile, it's not going to work, but we're going to provide what are known as function stubs. Function stubs are things that just print a message and don't do anything. Let you know that there is a function there and we're going to fill it in. Why do you create function stubs? So that your code can actually be compiled. My motto, compile early, compile often. We don't want to have to write the entire program before we can test it. So we have two functions here. What's the key word to define a function? DEF, sum loop, and it needs to take a variable, a parameter, It needs to accept an argument, so we're going to create a parameter variable. I'm just going to reuse the word limit. It's fine. And all this is going to do is print some loop called, and then return a 0. Obviously, that's not our final version of it. And let's write another one. Define some recursion, some rec, that's what we called it. Same business. All it does is print some rec called and return a 0. Now we can test everything. I'm going to delete my comments, get everything up on the top. And our recording didn't have the audio cranked all the way up. For those of y'all who are listening to this, prepare to turn your volume down. Alright, sorry about that. Okay. So I'm going to run it, and hopefully it'll just say sum up to what value, and then it'll say some loop called, some rec called. So, does the program do anything? No, it just asks for the value. It prints out a couple messages, and each function prints a message and doesn't do anything. But we have the skeleton in place, right? We can go in and we can put some good code here. Normally, to write a summation loop, normally to write a summation function, you just use a loop. So that's what we're going to do. We're going to use a loop. So we're going to declare a counter variable. I is a good enough counter variable name. And we're going to need something that contains our total. Total is equal to 0, and then we need a while loop. A while loop is like an if statement, except it repeats over and over and over until the condition is met. I'm pretty sure we've seen that already. So, while I is less than or equal to the limit, add I to the total, so total equals total plus 1, or total plus equals, not plus 1, excuse me. Total equals total plus I, or total plus equals I, my preferred syntax. And then we have to increment I. So I plus equals 1. Then run that. Type in like 5, because that's pretty easy for us to calculate in our head, right? 1, 2, 3, 4, 5. 3 is 6, 10, 15 maybe. Let's see if this works. Sum up to what value? 5. Oh, I've made a mistake here. What did I do wrong?
Still return 0.
Yeah, that's dumb. Okay, why don't we make that return total? And I don't really think we need this print statement anymore. That was just kind of to let us know that there was a function. Yeah, we could have done something like some loop unimplemented or supplemented, something like that. All right, now I'm going to do 5 again and hope that it comes out to 15. Okay, that works. Now we're going to write a recursive version of it. Recursion is when a function calls itself. And it sounds like an infinite loop, right? And it would be if you did this. Don't type this because this is bad. Define infinite. Like I said, don't type this. Call infinite. So if we ever called infinite, the very first thing it does is call itself, and it would do that until it crashed. Matter of fact, I'm going to put a call to it just so that we can see it crash. You see the error. And then I'm going to just delete all the work that I just did. Okay, so sum up to what value? 10. Boom, it eventually blows up. It says the previous line was repeated 990 more times. Maximum recursion depth exceeded. I don't know if y'all watch Doctor Who, but suppose that there was a door in the TARDIS that when you walked through that door, you walked back into the TARDIS. And so then you could walk back to that door and you could be inside the TARDIS a second time, and a third time, and a fourth time, and a fifth time. And then when you wanted to leave the TARDIS, you'd have to go back through that door once, twice, 3, 4, 5, and then you could finally actually exit it. Maybe that's a dumb example. But each time you call a function, you're inside that function, and if you call it again, you're down a level further, and then down a level further, and down a level further, and nothing ever returns. So that's a problem. We're going to delete that, delete our call to it, if you typed it in. So the way recursive algorithms are written are like this. I'm going to go down to the comments. To the bottom to add some comments, I think. Or maybe I'll just put them right here. Yeah, I'm pretty sure. Well, let's see. So the way recursion works is there's going to be an if statement. And the if statement handles one of two cases. Recursion if statement with two outcomes, states. One is called the base state. The base state returns a value. The recursive state returns a call to the function. So there has to be a way to get out of it. So that's why there's a base state. And then the recursive algorithm has to decide, okay, am I going to call myself or am I going to let myself return? What we're going to do is we're going to subtract 1 from limit each time we call ourselves. So the first time, limit's going to be 10. And then when we call ourselves, it's going to be 9. And then it's going to be 8, 7, 6, 5, 4, 3, 2, 1. Once we hit 1, we don't want to add anything, right? We don't want to add 0, not that that would hurt, or -1 or -2 or -3, stuff like that. So let's handle our base case. If the limit is less than 1, how about less than or equal to 0? Then we just return 0. That way, if they get funny and they enter a negative number as their limit, we're just going to return a 0. Else, and strictly speaking, if you have a return statement, else isn't necessary, right? Because either you return out of it or you do the next statement. But I kind of like the word else because it kind of implies the two states. So, just for debug purposes, let's do this. Let's print limit times asterisk. That way if they pass in 10, we'll print 10 asterisks. Something like that. We don't need that. We'll take it out. And then we're going to say return the limit plus the sum recursive version of our limit -1. And it's okay if you don't really grasp this, but I want you to have kind of an idea of it. Recursive algorithms are used to to do sorting and to crack encryption, things like that. They're not just something that you use to do accounting programs and things like that. But they are capable of solving complex problems. So if you go on and learn more complex programming techniques, this is one of the ones that you're going to learn. Now I don't want to make the same mistake. I don't even need a return there, do I? Because I already have a return here and I have a return here. So I'm going to get rid of that last return statement.
On the sum loop function, did you take out the print statement?
I did, yeah. So I've taken the print statement out of both of them. Certainly would be a good idea to take it out of SumRec, because if we called ourselves, if it looped 1,000 times, we wouldn't want to print it 1,000 times, although we're going to do that here anyways. But that's just to kind of prove a point. We'll delete that in a minute. Let's run it. Let's hope it works. Sum up to what value? 10. So why did we get that cute little pyramid of stars? Well, the first time we called ourselves, our limit was set to 10. And then we called ourselves with limit -1. You remember that in our code, right? So it printed out 9. And then we called ourselves with limit set to 8. And then 7. And then 6. And then 5. And then 4. And then 3. And then the 2. And then the 1. And then we hit the base case. And after the base case, you know, we were 10 levels deep into our returns, but that trickles all the way back out. We'll do another recursive program next week or so based on graphics. We did a tree recursion, I believe, in if you took one of my 103 courses. Not everybody did with me, so it may be new to y'all. And we'll see what else we can do with it. But I think that's enough for now. I don't even recall if recursion is discussed in our Python for everybody. Probably not, because it's not a Python concept, it's a programming concept, right? You can implement recursion in any language. So, I think that's about enough of that. I'm going to go ahead and make a Dropbox just for the recursive program. So there's a Dropbox for it. You may as well go ahead and close that script and upload it. So something that you may have noticed is that when you download your program, it runs it, right? If you download a PY file and then you double click it, it runs it. So, for example, if I was going to grade one of these and I grabbed somebody's program, downloaded it, it runs it. You may be downloading your program and wanting to edit it, right? So let's fix that if we possibly can. And this is for the Windows users. I don't know how to accomplish the same thing on Mac. I'm going to go into my scripting directory. I'm going to right click on one of the PY files, any of them. And only do this if you really want it to launch the editor when you click on a PY file. If you actually, have a whole bunch of Python programs you run, you probably don't want to launch the editor with it. You probably actually want to run the program. But do this. Right click on one of your PY files, do open with, and we want to browse and find a different program. Let's see if we can find idle. Oh, for Pete's sake. This may be a hopeless exercise if it takes too long to find it. All right, maybe it's in this directory for y'all as well. So you right click on it, choose Browse, see if you can find it in Program Files 86, Python 36-32, and then we actually want idle, which is stored in a subdirectory. I forgot which one. There we go. Well, they're not a far away. All of a sudden I found it everywhere. So anyways, it's in Program Files 86, Python 36-32, lib, libs. I'm failing to do this. Oh, really? Okay, this was a failed effort. Lib, idle lib. Idle PVW. Alrighty. Same path we've been. Lib, idle lib. Why am I not seeing it? What is my problem? Okay, my eyes were crossing. I'm sorry about that, guys. And then idle.pyw. And then click that. Now, hopefully, when I launch, really, when we installed idle, it should have put a open with idle option right there, and it didn't. Okay, once more with feeling. Browse, same business. I think I'll edit all this out of the video. How about that? Idle lib. How about just idle.bat? And it should bring up the editor with it at that point. So you want to open it with idle.bat. You want to configure it to open idle.bat. And if you double click on it and it still runs it, you're going to want to configure idle, and one of the choices is open in editor rather than open shell window. If you like opening idle and seeing the shell window, and I'm going to leave that, that's fine. But if you want, every time you open idle, it could instead be right inside the editor. And you can pick those, which ones you want. So why do you do that? So that if you download a PY file and you double click on it, it doesn't run it. Not a bad idea, because if you didn't write the Python file, you may not want it just recklessly running and having it delete things or whatever. All right, enough about that. So iterations. We just did an iterating program. We used a while loop. So a common pattern in assignment statements is when you assign something to itself. Get the current value of x, add 1, and update x with the new one. And we already know how to handle that. X equals x plus 1, or what's our alternate syntax that we like?
Plus.
Yeah, plus equals. X plus equals 1. Adding 1 to it's called an increment. Subtracting 1 is called a decrement. And of course, x plus equals 1, you could replace the 1 with any value. You want to go up by tens or hundreds or whatever. So the while statement. What you do is you write while, and then there's a condition after it. If that condition is based on a variable, you have to define that variable beforehand. You can also be sneaky and just put while true. If you put while true, there better be a break statement somewhere inside the loop, or else it's going to repeat forever. It's going to be an infinite loop. So this is a silly little program. It starts off at 5. It prints 5. It subtracts 1. It's still greater than 0, so it prints 4, subtracts 1, and is now 3. It prints 3, subtracts 1, prints 2, subtracts 1, prints 1, subtracts 1, and then it stops. Because n is equal to 0, so n is no longer greater than 0. So just like an if statement, if this condition is false, it falls through, and it prints blast off. Okay, and this is just totally for fun. Got it. So an infinite loop. An endless source of amusement for programmers is the observation that the directions on shampoo, endless amusement, lather, rinse, repeat, are an infinite loop. You'll never leave the shower if you follow those instructions. There's no iteration variable telling you how many times to execute the loop. There's no if condition saying that if you run out of shampoo, or if your hair is clean, you can stop. I don't know if bottles still say that anymore. Don't people know how to use shampoo? Why would there be instructions at all? I guess for legal purposes, so that people don't drink it or whatever. So in the case of countdown, we can prove that the loop does terminate. We know that the value of n is finite. We see that it gets smaller each time. Eventually we will get to 0. Other times a loop is obviously infinite because it has no iteration variable at all. You could write a loop, don't type this is stupid, that look like this. If 3 is while 3 is less than 4, print neat. Alright, if it'll loop. Why? Because 3 is always less than 4. The condition is always true. So to bail out of an infinite loop, you can put in a break statement. What a break statement is it's something that will stop the infinite loop. I'm going to just call this one September 14 without the R extension, or whatever you feel like calling it. So they already showed us one infinite loop. N is equal to 5 while n is greater than 0, print n plus equals 1. That's your classical loop. Now we're going to do the same thing, but with a break statement to stop it from being an infinite loop. N is equal to 5 while true. True has to be capitalized. I always forget that. Print n plus, this should have been minus equals 1. What have I done wrong here? It's always going to be greater than 0, right? So make that minus equals 1. That rocket crashed. So there we go. N plus equals 1 on both of them. So this is going to print 54321. I did plus equals 1 again. My brain's on pluses. And then this is going to print 54321, but it's not going to stop, so it's going to go negative very quickly. Missing parentheses. Oh yeah. Python 2 supports that syntax. Python 3 does not. We use Python 3. We need our parentheses. Okay, it's an infinite loop. I did while true, so obviously the condition is always true. But what we could do is after we subtract 1 from n, we check. If n is less than or equal to 0, break. I could just put equals 0, right? But I like making it a little bit more fail-safe so that if n came in there with a negative value or something like that and I didn't want it to keep running, it wouldn't. And there we go. So we've turned what would be an infinite loop into something that works just fine. Now in olden days, before you had sophisticated languages, you would implement things like this. I'm just going to pretend I'm writing BASIC on my VIC-20 or something like that. You'd say n equals 5, and don't type this, this is absolutely not going to work. Print n minus equals 1, and if n is greater than 0, go to 20. Like that. You use go-to statements. And that logic is actually kind of seductive, right? You see exactly how that works. But, and you can implement that in while loops, whereas there was, no while loop in machine language or in assembly or anything like that. But go-to statements lead to incredibly complex code. And a great many languages no longer support go-to statements at all. I don't even know if it's a keyword in Python. I'm going to type go-to, see if it lights up in purple. No, no such thing. So you'll see me use while true a lot. And I use while true when I don't want to bother to initialize and define a condition beforehand. What do I mean by that? Suppose I'm writing a game and I just want it to keep repeating until they choose no. Maybe I don't feel like defining the variable that'll let that happen beforehand. So let's give an example of both. So let's make a variable called repeat, and we're going to set it equal to y, and then we're going to do while repeat equals y, colon, print fun. That's our game. And then we're going to do repeat equals input. Do you want play again? Yn. All right, that's all well and good. The alternate way of doing it would be this. While true, print, and this is the game section of it, even more fun. Too much fun for one person to handle. Repeat is equal to input, play again, y/n. And then if they say if repeat is equal to no, or you say if repeat not equal to y, break. The second one actually looks a little bit more complicated than the first one, probably. But we may run up into a circumstance where it seems like the first one, where the second one is a better idea. And when is that? That is when we're reading data and we're not sure it's good or not. Typically what you have in that situation is something known as a priming read. The priming read gets a piece of data, checks to see if it's good, and then has a while loop inside it after that, where you do something with that data and then you read it again. So it's syntax is, its structure is like this, and this isn't going to be code, this is just going to be comments, but priming read, get a piece of data. While data is valid, it's not equal to 0 or something like that, do something with it, and then read, get a piece of data. Now that's okay, but you have two different places where you're doing your read, right? Sorry, not read, right. Two different places where you're doing a read. Yes, you have one there and you have one there. I don't particularly like doing it like that because this getting a piece of data may be 3 or 4 steps, not just one. Right? You may query the user for something and then you have to pass it into a function to convert it, and the function decides whether it's valid data or not or whatever. So if I have to do something like that, I avoid the priming read and I write it like this. While true, read, get a piece of data. If data is invalid, break. Should have made that a comment. And I'm not going to even put the else, because just like the return statement, if you don't do the break, you're going to do the next thing. And then do something with it. So at the expense of having 2 layers, nested layer, we have one nested layer here, and then we have an if inside that. That's the price for doing it like that, but the advantage is that we only have one read. And I would prefer to have the read only one place in my code rather than twice. That may seem a little bit abstract and it's not going to be asked on an exam, but just going to try to reinforce that there's more than one way to write a loop. A lot of folks won't even show you while true, but I find it a very useful mechanism. Doesn't make me better than, I prefer to avoid priming reads. And all textbooks tend to show you the priming read method of doing it. So here we go. Line is equal to input, and if they type done, break, else print the line. Alrighty. Hello. Hello. What's up? It ought to print it with an exclamation mark after it or something, right? And then done. Okay. So it just kept looping. Asking for data, doing our read. If we had been doing the priming read, it would be something like this. Line is equal to input. Present them with that cursor. They have no idea what they're doing. And then while line not equal to done, do something with it. And then get that input again. Line is equal to input. Pardon me? Thank you. Thank you. Yeah. All right. So there we go. That would do the same thing. Logically, they are equivalent. Like doing it like that? That's totally cool.
So you don't need to put a break done because you put when it's not equal to done. So as long as you type in done, it's going to basically treat that the same thing as a break.
Exactly. Right. Whenever the while code hits the first unindented line of the code, this condition is rechecked. And if the condition is now false, it just goes and executes that unindented line. Otherwise, it jumps back up here and repeats that. Kind of like our go-to statement. Did I delete the go-to statement? I probably did. Yeah. Anyways, so as it's running along a while loop, what it does is it executes all of the indented lines, and then when it hits the first unindented line, it jumps back up here, reevaluates, and if that condition is now false, it goes ahead and does the unindented line and goes on its merry way. I'm pasting this into the notes. You don't have to. I think that's it. So this way of writing while loops is common because you can check the condition anywhere in the loop, not just at the top. And you can express the stop condition affirmatively. Stop when this happens, rather than negatively. Keep going until that happens. So another reason to write it like that is you can have more than one stopping condition. You could run into an error state. And don't, I'm just going to open a comment. While true, do some stuff. If something goes wrong, break. Keep doing stuff. If something else goes wrong, break. Do the last stuff. If it went wrong, break. Like that. And maybe that looks silly, but say you had to open the file. This program is going to open up a series of text files and read them in. So do some stuff. Well, the file name is invalid, or the file is locked. It can't open the file, so break, leave it. Keep doing some stuff. Open the file. Or we've opened the file. Now read all the data. Say the read fails, then break. Do the last stuff. Process all the data in it. But if you get some bad data and you need to stop processing, then break. So you can have a whole bunch of ways out of it that would be just about impossible to express. No, it wouldn't be impossible to express, but the logic would be a lot nastier. While okay, or yeah, let's just use while okay. Do some stuff. I should just copy and paste this, but if something goes wrong, okay equals false. Else, do some more stuff. If something else goes wrong, okay equals false. Else, kind of see where we're going with this. Do the last stuff. If it went wrong, okay equals false. And then print. Whew, that's ugly. Which one of these looks cleaner to you? It's not really a trick question. Because this is totally valid, a totally valid way of working. And what I mean by trick question is there's no wrong answer. Maybe this makes more sense to you. It's a totally valid way of coding it. This is what clicks with me. Alright, I'm probably done with my comment. Finishing iterations with continue. Continue is another word like break that modifies the behavior of the while loop, but instead of exiting the loop, instead of going down to the bottom and continuing on its merry way after the loop, it jumps back up to the top and reevaluates right on the spot. So we're going to write a loop that uses continue. And it doesn't have to be an infinite loop in this case. N is equal to 1. While n is less than 100, print n, why 100? That's a bit excessive, right? 10. And while and then if n%2 is equal to 0, if it's an even number, let's do something else. Or let's continue. Else we're going to do something else. But we don't need to put the else, because the continue statement, anything after it, if we don't do it, we're going to keep going on our merry way. Print, I guess that was an odd number. Could we have worded this in a different way? Absolutely. And I am missing something, by the way. Without running it, I see what I need to do. What have I done wrong? Yeah, I'm not iterating it. So n plus equals 1 there. But that's wrong too. Because it would continue, it would go back up here, and that would be an infinite loop. So let's iterate it right off the off the top. Move that n plus equals 1 to the top, and then let's start counting as 0 instead. Now I believe it is going to copy print 1 through 9. Maybe. Oh, I have all that nonsense I put in there about play again, yes, no. And then typing in done. Then typing in done again. All right, there we go. There we go. After all that, you type in no 2 times. You type in done 2 times. We see our output. It prints 1. I guess that's an odd number. Then it prints 2, but it doesn't print. It's an odd. 3, I guess that's an odd number. 4, no comment. 5, that's an odd number. 6, no comment, and so on. So you see what continue is doing is like a go-to statement. Go back to the top is what it means. So continue. Go back to top. So here is an example of a loop that copies its input, in other words, I guess it just prints it back out, until the user types done, but if they start the hash character, then they don't print it out. So in other words, if they've typed in a comment, it doesn't print it out. So here's what they do. They get their input. If it starts with a hash, in other words, if the first character in the line is a £, then continue. Don't do anything else. And then if the line is equal to done, break. Now they could have switched the order of those two and it would behave just the same. Hey, come back. Otherwise, print the line. And I'm going to tack on the exclamation mark because I like seeing that it did something different. Alrighty. So, hello. Hello. Goodbye. Goodbye. Comment. What? Jane, stop this crazy thing. Done. Like that. So you get the idea of continue. Do I use continue a super duper lot? I can't say that I do. Doesn't mean you won't. So what do you use while loops? While loops are when you really are for when you don't have a defined series of values to step through. And in the case of most of the loops we've been writing here, we have had a defined series of steps to go through. 1, 2, 3, 4, 5, or 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Those are definite loops. We have a defined series of values to step through. So there's probably a better way to do that. We could use what's known as a for loop. And these texts always give an example involving lists, even though we haven't talked about lists yet. But here's an example. Friends is equal to, and then they have 3 friends. For every friend in the friends list, print Happy New Year, friend, and then print done. So it's iterating through a list, a predefined list of values. And you can do the same thing with numbers using the range statement. I hope they talk about the range statement. I'm going to screw down. Oh, of course we don't. They do it with a list instead. Whatever. Okay. Let's do that. No, let's not do that, because what if our list was 100 numbers long? I don't feel like typing L is equal to 0, 1, 2, 3, all the way out to 100. So if we were going to print out hello 10 times, it would look a lot like these loops we've been doing already. Let's do it both ways. N is equal to 0 while n is less than 20, because we're going to print it out 20 times. Print hello, and then n plus equals 1. That's one way to do it, and it's a totally valid way of doing it. And as a matter of fact, anything you can implement with a for loop, you could always do with a while loop. But here's what a for loop looks like. For n in range, going up to 20, up to but not including 20, print hello.
Would there be a reason why you want to do one over the other?
In this case, the only reason I would choose the second one is because I can type it in 2 statements rather than 4. And maybe that sounds silly, but you saw me already write code where I forgot to iterate the variable, right? It's a real drag to run something and to have to answer 17 questions and then just find out that you forgot to iterate your variable. For loops do a lot more than just counting through range statements, though. For loops make it really easy to do list processing. Let's go ahead and play with lists, since the textbook was rude enough to introduce them before we had learned about them. We're going to make a list of numbers, and just type in a whole bunch of numbers separated by commas. Doesn't matter what numbers. Don't type in the same one as me. So that's our handy list. We're going to do it both ways now. Let's declare a counter. N is equal to 0 while n is less than the length of the list, colon. Let's get a value out of the list. How about v? V is catchy for value. And by the way, I make list uppercase. It's my only exception to always using lowercase variables, because otherwise it looks like a 1. And then n plus equals 1. And we didn't do anything with the data, so let's print it out. Print v. That should print out all of our numbers. Now we're going to do the same thing with the for every value in the list, print that value. And that's it. Those two sets of code do the same thing. Again, one way is not better than the other. Technically, they do the exact same thing. And there may be times when you need to do the first one, and that is if you actually need to change the values in the list as you're going. This does not let you change the values in the list. But other than that, this syntax is so clean, in my opinion, that I would greatly prefer to do that. So in my mind, anytime that I have a definite series of values, a definite list of data, anything that's already predefined or over a specific range, I use for. It's up to you. The range statement can be modified to go down rather than up. Range starts counting at 0 and goes up to but not including 20. If you didn't want it to start counting at 0, you could modify it a little bit. I could say, okay, I want you to go from 10 up to but not including 20. And if you wanted it to go by threes, you could say, okay, I want you to start at 10, go up to 20, and every time you do it, go up by 3. It's going to look a little, no reason to keep that in the code, but, Start at 10, go up to, but not including 20 by threes. What this really means is, once it's equal or greater than 20, stop. So it's going to be 10, 13, 16, 19, and then once it adds 3 to it again, it's going to be 22. Well, 22 is greater than or equal to 20, so it would stop. All right, we are about... There's a Dropbox G2. Go ahead and upload your daily work into that. And we're going to put due dates on the textbook chapter 4 stuff as well. So, any questions? Yes, sir.
Well, it's about the surface program.
All right, cool. Let me go ahead and stop the recording and stuff, and then I'll look at the Surface program with you.